first talk is by Chris Lovell called Introducing Flares, the First Light and Reionisation Epoch Simulation. So Chris, when you're ready, you can unmute and go ahead.
Okay, can everybody hear me?
Yes.
Great. Okay, thank you very much to the Steves and to all of the organizing committee for organizing this fantastic conference. It's a real privilege to be the first speaker and introduce flares, the first light and reionization epoch simulations. So this is work that's been done with a number of people on the left there at Sussex and further abroad, and also the larger Eagle collaboration. I'm just going to present the first results from this detailed in the archive link at the bottom left there. Next slide, please. So what is FLARES? FLARES is a series of 40 zoom simulations using the Eagle full hydrodynamics model. These are selected with a range of different overdensities. As you can see from here, this is the dark matter distribution in all 40 regions. So we pick underdense regions and a number of very, very overdense regions as well. And each zoom simulation has a radius of 22 megaparsecs. Next slide, please. So we select these regions from a large 3.2 gigaparsec cubed dark matter only box. So this has a resolution of 10 to the 10 solar masses per dark matter element. So it's quite coarse, but it's sufficient to resolve the large scale structure. These are selected at redshift 5, and you can see compared to the periodic Eagle volume, which is inset in red, and the periodic blue tides volume, we're able to sample a much larger range of different environments than in typical periodic hydrodynamic simulations. So the purpose of doing this is not only to study how galaxy evolution during the epoch of reionization differs in these very different environments, but also to combine these regions together to build composite distribution functions that can significantly extend the dynamic range compared to smaller periodic simulations. Next slide, please. So just looking at the raw number of galaxies that we get in our regions, on the left, you see a cumulative distribution plot against stellar mass. The dotted lines here show the periodic Eagle volume, 100 megaparsecs on a side. And the most massive galaxy in this region at redshift 5 is around 10 to the 10.5 solar masses. Whereas in flares, we are able to simulate tens of galaxies above 10 to the 11 solar masses. And at around 10 to the 10 solar masses, we actually generate 20 times more galaxies at that mass. So we're producing a huge number of galaxies that are interesting to study. But if you look at the figure of merit on the right, so this shows the dark matter resolution on the x-axis against the simulated volume for a number of different simulations, hydrodynamic or not. And there's a general trend between the size of the resolution, size of the volume you can simulate and the coarseness of the resolution you have to deal with. So flares is done at the same simulation as the periodic Eagle volumes, similar to illustrious and to blue tides. However, by combining these together with the, to mimic the effective volume of the 3.2 gigaparsec box, we're able to significantly extend along the y-axis. Next slide, please. So which regions did we select and how do we combine those? So we selected a range of different overdensities shown on the left. We measure the overdensity on a very fine grid throughout the 3.2 gigaparsec volume, and then selected those with quite low underdensities in void regions, a number of mean density regions, but with a particular focus on these very overdense extreme environments as well. So the plot on the right, the solid line shows the distribution of overdensities in our flares regions, and then the blue histogram shows the overall log normal distribution of overdensities throughout the box. And we essentially weight these by combining them and weighting their fractional contribution to that overall distribution. If you're interested in the details, please refer to the paper. Next slide, please. So what does this look like in practice? So this is the galaxy stellar mass function on the left in flares from redshift 5 to redshift 10. And you can see there's a very strong double Schechter-like shape to the mass function, even up to these very high redshifts. And the characteristic mass, or the knee of this, it actually evolves with redshift from around 10 to the 9 solar masses to 10 to the 10 solar masses. And compared to the periodic eagle volume, which is shown on the right, so the dotted lines here are the measured double Schechter in flares, and then the points here are the measured stellar mass function in the periodic volume. The exponential tail is completely unprobed in this periodic volume. So it shows the value of incorporating these overdense regions to actually probe this tail. However, at the low mass end, the slope is actually in good agreement with the periodic simulations, which gives us some confidence in our weighting procedure. Next slide, please. So compared to the observations, flares kind of sits between the interstudy scatter, even up to the highest redshifts. Unfortunately, they're unable to completely probe whether this strong double Schechter extends to higher redshifts. However, compared to other models, such as blue tides and some of the semi-analytic models and the fire simulations, we don't see this strong double Schechter shape in those models. So we see a more power law-like or single Schechter-like shape. So one explanation for this may be that these very overdense regions that we're able to capture with flares contribute significantly to the high mass end of the galaxy stellar mass function. And these sorts of regions are simply not captured in these lower volume simulations. Next slide, please. So we can also look at the star formation rate function. So it's shown on the left. It also shows a very strong double Schechter-like shape. However, the characteristic star formation rate does not evolve with redshift in the same way as the characteristic mass in the galaxy stellar mass function. And this is telling us something about how feedback works in the Eagle model at high redshift, and it's something we're investigating now with relation to the halo mass function. So compared to the observations, we see slightly more tension at the, oh, gone too far. Compared to the observations, we see slightly more tension at the high star formation rate end, slightly higher normalization. But at higher redshifts, the observational constraints aren't enough to rule that out, sort of thing. And compared to the modeling constraints, we again do not see this strong double Schechter shape. But again, this may be due to the lack of these very overdense regions probed. Next slide, please. Oops, I think we've missed a slide. Thanks. So not only can we combine these regions together, but we can also look at the overdensity distribution. We can also look at the dependence of these distribution functions on overdensity. So the left two panels show the galaxy stellar mass function, and the right two panels, the star formation rate function. And there's a general trend with normalization and overdensity as expected. We also see a strong dependence on the form of each of these distribution functions, where the most overdense regions tend to show this stronger double Schechter shape. And it's these regions that tend to dominate the number densities at the very high mass or very high star formation rate end. Next slide, please. So finally, we also looked at the star forming sequence. So on the left, you can see there's a general decrease in the normalization with decreasing redshift as expected. We also measure a very strong double power law-like shape with a turnover that evolves similarly to the knee in the galaxy stellar mass function. However, we don't see any dependence on overdensity. So even the most overdense regions, whilst extending to higher stellar masses, do not show any difference in the star formation rate at fixed stellar mass. And this is in agreement with a number of observational protocluster studies at slightly lower redshifts of 2 or 3. Next slide, please. I think we skipped one. So that was the flares, first light reionization epoch simulations. I think we've gone back again. But essentially, yeah, just like to wrap up there. And you having trouble, Steve? There we go. Don't click anything. Okay, so I'm just going to wrap up there. If you are interested in reading up on some more details, then you can find them at the archive link on the bottom left. We also have a website, flaresimulations.github.io, where you can find more information, visualizations, and data products. In the future, we're looking at some of the passive population at the high redshifts, galaxy sizes, a number of predictions for the upcoming Euclid and WFIRST observatories, and some of the black hole properties and other things. But if you're interested in any of the data products from flares, then please do get in touch. Happy to make things available, and we'll be releasing data products in the near future too. And Ashwin should be up next showing results for the UV luminosity function. Thank you very much.
All right, thank you, Chris. So I had one question before I lost my ability to see Slack, which I'm working on, but the question was from Aaron Young, and he was asking if you could talk about why you see this double Schechter function at higher redshifts, so where you think you see this.
Yeah, so the Eagle model, essentially has two forms of feedback, AGN and star formation feedback. It's obviously not expected that AGN feedback plays a very strong role, particularly at redshift 10. However, there is a temperature dependence to that AGN feedback in the model. And at these high redshifts, where the temperature, the overall gas temperature is a lot lower, the actual AGN feedback may be a lot stronger at lower masses. So this is something we are actively looking at, but it's still kind of up for debate at the moment, but very, very interesting. It may be something particular to that AGN feedback in Eagle at these very high redshifts.
Okay, thank you. And then a follow-up from Tom Thunes. He said, if presuming the exponential cutoff is due to AGN feedback, have you looked at the AGN luminosity function?
So that is something we're looking at now. So Steve has a student who's studying the AGN luminosity function, very much in early days with that at the moment, but it's certainly something we're very, very interested in to try and link to this double Schechter shape that we see in the galaxy stellar mass function and the star formation rate function for sure.
And there's a question from Anna Schauer who asks, what star formation models do you use? Do you include population 3 stars?
So we do not include population 3 stars. At the moment, this is essentially using a slightly different calibration of the Eagle model called AGN DT9, but it's essentially very close to identical to the fiducial Eagle model. So it was tuned to the z=0 galaxy stellar mass function and also to galaxy sizes at redshift 0. But aside from that tuning, the model that we use was not tuned at high redshift, so all of this is predictions at high redshift. However, it doesn't include any particular population 3 like extra modeling or anything like that. This is the vanilla Eagle model. So it's interesting to see how well this does at these epoch of reionization kind of eras. I don't think the resolution is particularly good enough, for example, to resolve the kind of population 3 star formation at slightly higher redshifts. But that's something we'd definitely be interested in future iterations of the model, where we're going to look at increasing the resolution and studying some of the first stars.
Okay, and a couple more questions about the missing double Schechter on the observational side. So from Enrico Garaldi said, you mentioned it may be due to the larger volume probed. If you restrict flares to a smaller volume, do you still see this double Schechter?
That's a good question. So it's a kind of a trade-off, right? So if you restrict the volume, unfortunately, you then you're not able to include those very, very overdense regions simply because you're using a smaller periodic volume. So there are, so in the periodic 100 megaparsec volume, you only get 2 or 3, greater than 10 to the 14 solar mass clusters at redshift 0. So those protocluster environments at high redshift aren't very extreme. So there's this kind of trade-off between, you go to this very, very large box and you're able to capture these protocluster regions, but you can't.
Okay.
Yeah, I think I can see what you
I'll
mean.
give you one last.
Oh, go on.
Oh, sorry, I was going to give you a follow-up, but go ahead and finish.
No, go for it.
Okay, so one last one about the double Schechter, and then we'll move on. This is from Christian Finlater. Christian says, the double Schechter form looks as though it might reflect reaccretion of expelled gas into massive halos. Can you run a no wind model to rule this out?
That's interesting. Yeah, so we're looking at some of the modifications to the AGM feedback, but some of the star formation feedback was not high on our priority list. But if that's something that there is maybe evidence for in some of the higher resolution Zoom simulations from other groups, then that would be super, super interesting.
Okay, great. Well, thank you, Chris, very much.